I'm here in California, where I've been speaking to many of the world's leading experts on satellite technology, on the future of satellite technology and its role in the digital world. And we can expect 15 to 20% revenue growth in satellites. 28% of that will be on of the extraordinary 123 billion spent last year was spent on things like ground equipment. 9% was on satellite manufacturing. 3% was on getting the things up, launching them, and 60% was on associated services. And we could expect around 110 satellite launches every year, of which around half will be commercial. We'll see very big growth in just about anything and everything associated with satellites, because our world is hungry for more data. And you will see rapid growth in things like the terminals, the gateways, the communication systems, handheld phones, global positioning systems, and just about everything you can imagine. If we look at just satellite TV, by the end of 2006 we had around 89 million people watching satellite, and now it's around 100 million by the end. It was just within about 18 months. Satellite radio has jumped from 14 million to 18 million in the same period, and we can expect in the future that mobile data connections will also grow quite rapidly. Now, the nations that are leading the way are the United States, we've got the European Union. Then there's Russia, China, India, Canada, Japan's got a good satellite program, South Korea, Israel, Brazil, and so on. And yet, all of these communication methods are subject to certain vulnerabilities. And satellite is in competition in part with big cable. On February the 1st, 2008, 3 big cables got cut accidentally by dragging anchors in the middle of a storm and various other problems. And 75% of all European and Middle East communication capacity was lost between those two. Of course, we also saw in the same year months of disruption in East Asia. But you know what? 25 large ships are constantly working around the world to repair these cables, and it's only when several go out in the same area that you even notice a problem or it gets reported. In the Atlantic alone in 2007, there were over 50 major repairs of transatlantic cables. A tiny proportion of the service went out and no one noticed anything. But while cables are vulnerable, and they're also vulnerable on land to just cutting maliciously, criminal activity, or accidentally, but satellites are also vulnerable. In the area where geosynchronous satellites work, that is, let me explain that. Those are satellites which are 36,000 kilometers above the surface of the Earth. That's a long way, 36,000 kilometers. At that point, the gravitational pull to the Earth is relatively small. And the satellite can do exactly one orbit a day at that speed, at that height, and still remain in orbit without falling down to Earth if it travels too slowly, or spinning into outer space if it was to travel too fast. And that's exactly the point where the gravitational pull and the satellite speed are in balance. The satellite speed is constantly trying to pull it out, and the gravitational pull pulling it in. 36,000 kilometers from the surface of the Earth is exactly the right place. And that satellite, if it's launched above the equator, will remain directly above the equator, well, for maybe 10 or 15 years, with very small adjustments made in terms of the positioning of the satellite, just stopping it from twisting or turning if it's hit by a small amount of debris and so on. But there are 24,000 man-made objects already in that space, and these, I'm afraid, can kill satellites. On the 29th of March 2006, the Express AM-11 satellite, a Russian satellite, was killed off by space trash, and then its small jets had to propel it into an outer orbit, and so it would drift off into outer space. We didn't want it coming back to land, and we didn't want it colliding with anything else. So what about the future demand for satellites? Well, that will be driven in part by demographics as well as by technology. By the 1 billion children alive today, all of whom will be adults in 15 years' time. By the 1 billion adults who will acquire mobile phones for the very first time in the next 2 to 3 years, almost all of them in emerging markets. It'll be dictated by the 300 million adults that will move to cities in China by 2020, looking, many of them, for digital services. It'll be dictated in part by the 748 million Africans moving to African cities by 2020, again, many of whom will come over the following years to look for all kinds of communications equipment. And what do people want? Well, I guess it's unlimited bandwidth, so we can surf wherever we are, online all the time. at low cost, very low cost, and no real interest in how the bandwidth actually arrives. Simple and reliable. It really is that. So what about alternative technologies to satellite for people who want data connections? There's a local wireless loop, so-called the WLL, wireless local loop, but actually that's failed to take off as people hoped a few years ago. What is it? It's when you put a transmitter on the side of a local shop, and that transmitter connects to the local phone network, a big copper wire, or a fiber optic one, and from that transmitter you get lots and lots of local receivers using a little handset, a bit like the one that you might have in your own home, attached to an answering machine, but with a slightly longer range. Now, quite honestly, the take-up of that has been much lower. It's been a fraction, maybe 10% of what was forecast 10 years ago. And then along comes Wimax, so-called. Wimax allows us to have a transmitting station up to 70 kilometers away, but the maximum bandwidth in some of these systems is only about 70,000 characters per second, 70K. Again, the take-up has been slower than forecast, with only 800,000 users in the United States by the end of 2007. Nevertheless, Sprint has invested $5 billion in it, and others are doing so. And then there's been 3G, the so-called miracle of technology, which allows us to surf at speeds of up to 3, 4 or 5 megabits per second download, up to 750, 800K upload. But again, the take-up of 3G has been slower than forecast. And in Indonesia, for example, 1/3 of all handsets in 2008, which were able to receive 3G signals, were not being used for 3G services. What about high-density, high-definition TV? Well, certainly that is a massive area that's taking off. And it's an area which is very efficient for satellite. Here is a satellite which is receiving a signal 36,000 feet above the Earth, from a base station, from a TV station, up to here, not just to one TV channel, but maybe 30. And it's amplified by the circuitry in the thing, which is solar powered, and then beamed back right over the whole of that surface, a very wide surface of the Earth, can then receive those digital TV channels. And it's a very, very efficient way to use technology. And we can expect continuous growth, a rapid growth of high-definition digital TV channels by satellite. We can also expect satellite radio to continue to grow by around 30% per annum. We already, with maybe 40 million subscribers by 2010, again for areas where ordinary terrestrial radio just doesn't do it. At the moment in 2008, mobile satellite services, if you look at the actual use of that bandwidth, around 40% is voice, 60% is data. But you can expect that to change, especially with video streaming, which we'll come on to. When we look at satellite TV and digital radio, at the moment with these, the traditional geosynchronous satellites, these ones which stay in exactly the same position above the equator, 75% of all their bandwidth goes on satellite TV and digital radio. And I would expect that to fall to around 50% by 2015, 2018, as the growth of other online services increases. Now let's have a look at the total global bandwidth. If we're looking at that, if we look at the military, you'll find that the total military bandwidth has grown by about maybe 20-25% per year at times of conflict. But that's nothing to what you're seeing for global bandwidth for domestic and business users, which is growing by 43% per annum from 2003 to 2007. Now for the military, they calculate bandwidth on megabits per second per 5,000 people in the military, and it's running by 2008. It was running at around 100, 105, 110. By 2010, it may be 150 megabits per second per 5,000 military members. Now, when you're talking commercially, we do different calculations. But 2 young men, both of them under the age of 30, have been responsible for 10% of the entire bandwidth used in many developed countries. And they are, of course, the founders of YouTube, the largest TV station in the world, with up to 100 million uploads a day, 600 million downloads a day, and this is only the start. And while 10% of bandwidth in the United States, in America, in Canada, in New Zealand, and so on, in Europe, is from YouTube, in the UK, we've seen another phenomenon, which is the iPlayer, another version of video on demand. run by the BBC, launched on the 13th of December 2007, 100 million requests in the first 6 months, and the cost to the internet service providers has been extraordinary. They are complaining that they have had to bear $1.5 billion of extra capacity need in the first 12 months. Now, this stuff that's coming down the line, it was expected to be mainly stored programs, downloaded offline while people sleep, online while people sleep, but actually watched later on. But in fact, live video streaming is happening 8 times more often than stored watching. So people like to click instantly and to see the program happening frame by frame in real time, which poses an even bigger stress on the system than if the system can just download it quietly in between gaps in other traffic. So 5% of all UK traffic within the first few months, 10% from YouTube, that's 15% from just 2 new sites that have only emerged in the last 36 months. It's all part of the future, a future which will be dominated online by the video demand rather than by let's say email. Email, yes, it's grown a lot, but let's look at the facts. One single 2-hour video clip, or rather a program, one single 2-hour video is equivalent to downloading 200,000 text emails, each the size of around 25k. And that's because video requires half a megabit per second per person. That's 1.8 gigabits per hour. That's a lot. Now, there's another site which saw a huge explosion just during the Olympics in August 2008, and that was NBC Universal in the United States. 8 million US citizens watched the opening ceremony of the Olympics online from that particular website alone. That was 8% of the entire United States audience, and in addition, on mobile phones, another 500,000 people were watching. Now, what is truly shocking about that is that same program was available by satellite, being washed all over America for anyone who had a dish, and was also available through cable connections and through terrestrial broadcasting. But nevertheless, and you know what? 100 million people could have watched it from satellite without a single bit of stress and strain except on electricity usage. Electricity to power the receiver, electricity to power the TVs. But those 8 million that chose not to watch the signals that were already there, but chose to connect themselves individually to the NBC website and set in train a unique stream of data coming from that particular set of servers to their own computer. That put a colossal strain on the internet and was actually very expensive from the energy point of view. It was just an unsustainable activity, really. And to give you an idea of what we're talking about, the internet this year in 2008 will consume 1 trillion kilowatts of energy. What does that mean? Well, a kilowatt hour, 1 trillion kilowatt hours. A kilowatt hour is a single bar on an electric heater, or it's the number 1 click rather than the 2 click or the 3 click for boost on your fan heater. It's a heater running for 1 hour in your home. That's quite a lot of money. And it's equivalent to maybe, depending on the prices in your country, it could be 20 cents or more of electricity bill. And we're talking about 1 trillion kilowatt hours. And you know what? Every one of those kilowatt hours of electricity used online turns into one thing: heat. And that is why you've got huge problems with cooling of these web servers now. For people like Hewlett-Packard are having to invent new ways of cooling down their web servers so they don't actually melt, so they don't break down because of so much heat. So they're building heat exchange devices which suck heat out of the servers and pump it into local homes. That sounds a good idea, but it gives you an idea of the scale of this massive heat. 1 trillion kilowatt hours of heat being released just by people using the internet, and as we can see, most of that in the future will be video watching, and that's just today. 1 trillion kilowatt hours today. We could be talking up to 100 trillion kilowatt hours by within another decade, mostly video watching. And in comparison, the total bandwidth of all commercial satellites is relatively small, and when they're used to shine the same programs over a very wide area, as I say, it's very efficient. If we assume that the average satellite produces less than 20 gigabits per second, and there are only around 400 up there that are actually worth thinking about, The average satellite lives up there for about 10 to 15 years, 12 to 15 years before coming out of service. Then we'll be saying that the total bandwidth of all commercial satellites is less than one single huge cable. And if we look at the actual cost comparison, a new cable from Japan to the United States is costing around $300 million. It will be delivered in 2010, ordered in 2008. It will be able to carry 8 terabits per second. That's 8,000 gigabits per second. A gigabit is 1,000 megabits, and a megabit is 1,000 K. And around 25K is a single email. It's a lot of data, 8 terabits per second. That cable, which is 10,000 kilometers long, as I say, will cost around $300 million. That's around $35 million per terabit. Just remember that figure for a moment. $35 million per terabit. Why does it matter, terabit per second? I'll tell you why. Because the largest geosynchronous satellite, with 100 gigabytes per second, bought for $500 million, will cost around $5 million per gigabit per second, equivalent to $5 billion per terabit per second. What did I say the other one was? So a cable comes out at $35 million per terabit per second. A large geosynchronous satellite doing the same task of just linking 2 great big centers together as a virtual cable going up into space, 36,000 kilometers up, 36,000 kilometers down. That's going to cost you $5 billion, not $35 million. Not $35 million, but $5 billion for the same bandwidth. So you can see that even if the capacity and the doubles and the cost falls significantly, that you've got major cost differences between these two. Which is why you're not going to use it except to fill in things around where we can't use normal technology. Now, an area where we might want to fill in is in rural America. In rural America, we have 15 to 20 million rural households right now, which are poorly served by broadband. Over 1 million of those are using broadband satellite already in the United States by the end of 2008, and that market will potentially increase by another 4 to 8 million. And that'll be providers like Viasat-1 using KSAT systems, and I won't go into the complexities of it. But just one final thought. There is one technology which could dramatically change the landscape of satellites, and that is low-flying satellites. Now, low-flying satellites have a bad reputation because people tried them in the past with large systems, Iridium systems and others, and quite honestly, they didn't work financially. They were difficult to run. You needed mobile antennae which moved around. It was a nightmare, and those companies had huge financial problems. But there's a new alliance launched in September 2008, which thinks that they've cracked the technology problems and raised funds to do it. And they think they can roll out a new broadband system for the whole of Africa at the same sort of cost per user of ordinary fiber optic cable today. And they're planning to use low orbit satellites, whereas the geosynchronous ones go around the Earth in exactly 24 hours and stay above the equator in exactly the same position in relation to the Earth. These ones are at only 8,000 kilometers height, not 36,000, so they have to whiz around the Earth to stop themselves from burning up. And they will go around the Earth every 5 hours. So you need a large number of them. You need 16, in fact, to provide reasonable coverage for Africa. You also need to receive, you need ideally 3-meter dishes. That's big dishes, really, if you think about it. 3 meters, that are you can't put those on a car. And these dishes need to have motors that can track the satellites as they move across the sky. They use the K-band system. You're talking about a fast, you're talking about high power, you're talking about a lot of bandwidth, you're talking about maybe 10 gigabits per second per satellite. And as I say, we're looking at comparable performance ideally to fiber in terms of cost. We're talking about a system which could shine a satellite signal on up to 300 base stations at once, scattered over a huge city or a huge country. And each of those base stations could be a 3G mobile phone center with no connections to the outside world except a satellite dish and a generator and a bit of diesel in there and a big tall tower with some aerials on the end. And so you could see that this system could allow very massive upgrades of existing telecommunication systems in places like Africa, where telecom companies are spending maybe 35% of all their costs simply maintaining telephone lines between one centre and another, or infrared links between one mast and another, and it all gets very, very, very costly. Now, this O3B, which is the other 3 billion people, that's what it stands for, the O3B network, is backed by Google, which has put in $10 million. HSBC put in $20 million. Liberty Global, they've also put in some millions of dollars. But they will need to raise in the open market at least 625 million more in order to make this project work. So we'll have to see what actually happens. But you know what? There's plenty of opportunity for them if they could crack it. In Latin America alone, take Brazil. It has 2,500 cities with no mobile phone service. 20% of all the people in 11 Latin American countries will need a government subsidy in order to get mobile services that they need. And how will governments do it? Well, they may well come to O3B to provide them some of the infrastructure behind in order to make these mobile telephone systems work. So, in summary, satellites have a great future, but they are expensive. They will be used to fill in gaps around the other systems which are there. The new generation of low-altitude satellites could take off and could provide a much-needed boost to infrastructure for broadband in places like Africa and Asia. We can expect a massive growth in the video online, video on demand, a huge growth in mobile services which have satellite contributing to the communication systems rather than being pure satellite phones. I think the phones will connect primarily to the local network, and then the local network will use satellite to make the bigger connections. There will be fierce competition for what we call the last mile, which is getting the signal actually into your home, into your office, using all kinds of different technologies. Satellite will be one, especially in rural areas. We'll be looking for everywhere all the time, and as I say, low orbit satellites could really change the rules of the game.